This week's lesson is on volcanoes. What is a volcano? A volcano is a place where magma reaches the Earth's surface. So as you can see here, magma is located in the crust of the Earth, all the way down close to the mantle. And that magma in a volcano goes up through channels that are formed in the Earth and erupts from the surface. The volcano includes the surrounding cone of erupted material. The cone would be the layers of material that have built up over time as the volcano erupts. And volcanoes form along plate boundaries or at hotspots in the mantle. Magma is what erupts from volcanoes through vents. Lava is magma that has reached the surface of the Earth. Lava builds up in layers as each layer cools to give the volcano a particular shape. And the severity of the eruption is dependent on the viscosity of lava. We're going to spend a lot of time today talking about viscosity. So what kinds of things can erupt from a volcano? All of these things are called pyroclastic debris. Pyroclastic debris is materials other than lava that has blown out of the volcano. These can be in the form of dust and ash. Magma explodes from the volcano and solidifies in the air as it cools very quickly, and existing rock can be shattered by the powerful eruptions. Direct measurements of pyroclastic flow, which is what you see in the background of this picture, are extremely dangerous. Let's talk about one of the most well-known and devastating volcanic eruptions that has happened in the history of the Earth. On August 24th, 79 AD, Mount Vesuvius, which is in Italy, literally blew its top, erupting tons of molten ash, pumic, and sulfuric gas miles into the atmosphere. The pyroclastic flow flowed over the city of Pompeii and the surrounding areas and killed all its inhabitants. Pyroclastic flows of poisonous gas and hot volcanic debris engulfed the cities of Pompeii, Herculaneum, and Stabia, suffocating the inhabitants and burying the buildings. And then these were later discovered by archaeologists, and those archaeologists then dug out, and this is what they found. Here's a little more history on Pompeii.
On August 24th, 79 AD, the city of Pompeii was entombed by a massive eruption from Mount Vesuvius. For 2 days and nights, the volcano rained terror on all those in its path, killing almost everyone in the city. After the eruption, Pompeii was lost and forgotten for almost 1,700 years. It's hard to imagine this entire city completely buried by volcanic pyroclastic flows coming down from Mount Vesuvius. But that's exactly what happened here in 79 AD. The city was completely covered in ash and cinders, preserving the city. And it actually gives us a really good glimpse into what life was like back in ancient Roman times. Pompeii was so perfectly preserved and so carefully uncovered that walking the streets here is a surreal experience. The whole city is a window into the Roman Empire, frozen in time, at the height of its power. 300 years ago, when the unearthing of Pompeii began, 18th century archaeologists made an amazing discovery. During the eruption, the population was entombed by the volcanic ash and pumice that rained down, and when the archaeologists started excavating the site, they found these empty spaces and they filled them in with plaster, and you can actually see the features of these bodies from the ancient Pompeians. volcanoes, it is very sobering to see the tragic results of being in the wrong place at the wrong time.
So that's what the city of Pompeii looks like now, and it gives you an idea of what it looked like at the time when people actually lived there. Today, Mount Vesuvius remains a hazardous volcano with heavily populated areas all around it. In the city of Naples, there's about 1.5 million people. Naples is only 30 kilometers from Vesuvius, so if Vesuvius were to erupt again, that city and all of the other cities in the surrounding area would definitely be affected. So how and why do volcanoes erupt? Well, magma, which is liquid, is less dense than solid rock, so it rises. This is the same principle as hot air rising, or, for example, how a hot air balloon works. The type of magma depends on the viscosity of the magma. Viscosity means a liquid's resistance to flow. It relates to how thick or sticky the liquid is. Large amounts of gas and a high viscosity or very sticky magma will form an explosive eruption. Think about shaking a carbonated drink and then releasing the cap. Lots of pressure has built up because of the high viscosity or the sticky magma. Small amounts of gas or low viscosity, runny magma, will form a nonviolent eruption. This is where the magma just kind of trickles out of the volcano and flows down the sides of the volcano. So do you understand? You choose the correct term. The higher or lower the viscosity, the thicker the thinner, or thinner the liquid, the more violent the eruption, which will result in the most violent eruption. If you said, the higher the viscosity, the thicker the liquid, the more violent the eruption, you're correct. The composition of magma determines whether it's explosive or not. This means what the magma is made of. There's a mineral called silica that determines how viscous the lava or the magma is. A high silica content is more likely to be an explosive eruption because silica has a thick, stiff consistency. It flows very slowly, and it tends to harden in the volcano's vent before it erupts, so then high temperatures and dissolved gases can build up behind that, causing lots and lots of pressure, and therefore a very explosive volcano. So, make sure you understand, more or less silica equals more or less viscosity. If you said more silica equals more viscosity, you're correct. There are three types of volcanoes: a shield volcano, cinder cone volcano, and a composite volcano. The first type is the shield volcano. These produce very nonviolent eruptions. They have very low viscosity of magma, and one of our most well-known examples are the Hawaiian Islands. All the Hawaiian Islands are actually shield volcanoes. Let's take a look. This says lava rivers on the Palama Pali at the 1,600-foot elevation just above the Royal Gardens. So you can see the lava is not exploding out of the volcano, it's just slowly flowing out. You could easily walk away from this lava and still be safe. So keep in mind this lava flows out of it's coming from the mantle of the earth, and when it reaches the edge of the island, it's going to hit ocean water, so it cools down very quickly. And as the lava cools, it forms a nice flat kind of island, or a nice flat volcano. So that's a shield volcano. The next is a composite volcano. Composite volcanoes are tricky because they have both violent and non-violent eruptions depending on what's going on down underneath the surface. You can find both low and high viscosity magma, and the shield or the cone of the volcano is formed by alternating layers of lava and pyroclastic debris. Remember, pyroclastic debris is anything other than lava that comes out of the volcano. Our most famous example that's nearest to us is Mount St. Helens. Mount St. Helens was a pretty big deal when it happened back in 1980. Let's take a look. This is Mount St. Helens erupting. This was May 18th, 1980. This is in Washington State in the United States. And you can see it didn't explode straight up, it actually kind of blew the side off the mountain. And here's a little more information about Mount St. Helens.
The eruption of Mount St. Helens on May 18, 1980, was one of the most dramatic geologic moments in American history. It was a Sunday morning, 8:32 a.m. Vancouver, this is it, was the excited call on the radio from David A. Johnston to his colleagues. Within minutes, the colossal eruption had caused hundreds of millions of dollars in damage, and 57 lives were lost, including Dave Johnston. For 2 months prior to that eruption, scientists with the U.S. Geological Survey and the University of Washington's Pacific Northwest Seismographic Network had been closely monitoring the volcano.
All the deformation on the mountain was local to the mountain, and even more local than that was on the north side of the mountain. In the nearly 2 month period before May 18, what was essentially happening at Mount St. Helens was that magma or molten material was moving up from some deep reservoir beneath the mountain up into the volcano itself. And it began to grow or form what we call a dome or a cryptodome inside the volcano. And that inflating body of magma or molten material actually broke the north side of the volcano and began to cause the north side of the volcano to expand out toward the north.
I mean, we're measuring the rate of northward movement of the faults at about 6 feet a day, and we knew that wasn't so good.
On the morning of May 18, I was driving up Interstate 5, headed up to the north side of Mount St. Helens with some parts and some batteries for our time-lapse cameras. And as I glanced over at Mount St. Helens, it was a beautiful blue sky day, and the mountain was sitting out there, and suddenly I saw this mushroom cloud go up above the volcano and climb rapidly up into the stratosphere. I was down in the room where the seismographs were at 8:32 in the morning, and I heard a sound, and I just looked over my shoulder, probably just a split second after the earthquake, the big earthquake had started, and saw that this was something very large, larger than we'd seen before. Watched it for a few seconds just to confirm that. And then I ran upstairs to the next floor up to the radio desk of the Forest Service and called Dave. And we couldn't get through. There was no answer. So I guess I had the realization right away that this was some kind of a tragedy. And on the one hand, it was this huge, exciting, and interesting magmatic eruption, and on the other hand, I was pretty certain that something terrible had happened to Dave. So it was a strange day for me. And we were off the ground probably at 9:05 or something like that. I mean, it was really, really rapid, and got up to the point where we could really see the mountain well, I suppose between 9:20 and 9:25, like that. There was this terrific, very vigorous vertical eruption column. There was the stem of the mushroom or the toadstool that blossomed out at greater height. And for most of the morning, we saw this tremendous ash cloud roiling out toward the northwest. And I can only assume that was coming off of the big pyroclastic flows that were going off in that direction that later built the pumice plain. It was a very eventful morning, but it was sobering because I remember thinking up in the airplane that Dave just couldn't have survived this, especially when we got around to the west side and saw all this ash headed in his direction. On the morning of May 18, what actually happened. The landslide basically uncorked this pressurized body of magma and allowed it to explode or expand out towards the north very rapidly. This is what we call the lateral blast. It was a horizontally directed explosion of incredible magnitude. It caused this expanding cloud of ash, rocks, and gases to move out across the countryside to the north at speeds of several hundred miles an hour. The directed blast was really the most destructive event that occurred on the morning of May 18. It completely destroyed an area of 230 square miles in the matter of somewhere between 5 and 9 minutes. It essentially killed every living thing within an area of 230 square miles, and it destroyed hundreds of acres of virgin forest, and it was an incredibly spectacular event.
We put on news stations, and we quickly started to remonitor the volcano again because we had no idea what was going to happen.
Before the dust had literally settled in the summer of 1980, there were USGS scientists swarming all over the area out in the blast zone, studying the pyroclastic flows, studying the debris avalanche deposit, studying the directed blast deposit.
We thought it likely that there would be more eruptions during the summer, and indeed that took place.
Suddenly this immense black eruption cloud came pouring up out of the white layer, the cloud tops, and I couldn't believe my eyes. I mean, I thought this is the most incredible thing I've ever seen in my life.
We learned a lot about how you interact with civil defense, with the public, with the press, and that was transferred by the press to the world. And as a result, I think volcanology took a quantum leap in science as well as applicability to society's needs.
The subsequent eruptions were actually, most of them were forecast fairly accurately by the USGS team of scientists. So when it looked like another explosion was about to take place, our helicopter crews would pick us up and we'd move out to the outskirts of the blast zone. We'd watch and photograph the next eruption. As soon as the eruption stopped, we'd race out there and study the deposits while they were still hot, while they were just after they'd settled onto the ground. So it turned out that the 6 years that Mount St. Helens was erupting in the early 1980s was an unprecedented opportunity for USGS scientists to study hot, fresh, young, and exciting deposits from explosive volcanism. We learned incredibly new and important bits of information about how volcanoes like Mount St. Helens work, what kinds of deposits are produced during these explosive eruptions, and how to anticipate and mitigate the consequences of explosive eruption.
So there you see the USGS, the U.S. Geological Society's take on Mount St. Helens. And our final kind of volcano is a cinder cone volcano. These are extremely violent eruptions. They have very high viscosity magma, so that pressure builds up underneath the surface until it finally explodes. And the cone is formed by pyroclastic debris. Here's an example of a cinder cone volcano in Mexico. This is Mount Pyroclastic. So you can see that's a much different kind of eruption than the Mount St. Helens or the Hawaiian volcanoes. And you can see that the cone of the volcano looks significantly different than those other two as well. So that's a little bit about volcanoes. For the rest of the week, you'll be learning a little bit more about how volcanoes work and whether we can predict a volcanic eruption. As always, if you have questions, please send me a message.